Recording
So
is on.
William Log. In the background, we have some open sourcing work on a simple extruder for the 3D printer. So simple 3D printer extruder. So the OSE club at the London International Academy, they've been working on various things. Part of it is the filament maker. Part of it is open sourcing a very simple extruder. So as you see here, let me maybe share my screen. This is work straight from London, Ontario, Canada with William Neal. So here's an example of a 3D printer extruder, a very simple one for 1.75 millimeter filament, which you can basically 3D print from the white printed pieces. There's a spring, there's a drive wheel, little bearing, and then a little metal part. But we're open sourcing that, so William's going right ahead on that. So reverse engineering, taking apart that extruder. And why? Why do this? And then, okay, from taking dimensions into CAD. So this is now in FreeCAD, and including the aluminum heat block, X-axis bracket. Oh yeah, so this is how you mount this to the guide rails. But the idea here is for William, he's had really nice success with this particular extruder, and that he said he had to clog up only like a couple of times in a couple of years. So a very good track record. So we decided to open source that, make it a low-cost version that we can do as well. That's pretty good work. With respect to the aluminum part, if we don't want to go into buying aluminum stock, we can do, like, for example, I don't know if anyone's heard of zinc aluminum alloys, but if you mix zinc with aluminum, where you have mostly zinc, which is a low temperature melting metal, melts at about 420 Celsius, if I recall correctly. If you mix that with aluminum, you can have an alloy that's as strong as aluminum, but melts at a low temperature, which is going to be about, I believe, 500 Celsius or so, meaning that you can do this on a stovetop foundry, meaning you get yourself a pot, cooking pot, put the metals in there, they will dissolve, they will melt. Then you can cast that if you want to do that. So I brought up the concept of MIG casting. Well, you could do MIG casting. You can also do this pour from a stovetop foundry if you want to reverse engineer this kind of a little simple extruder with metal parts. So that's, if you want to see more details on that, I put some information on zinc aluminum alloys, ZA alloys. It's interesting because, or we can say stovetop foundry. Interesting because, okay, we talk about the induction furnace all the time. Let me look at the recent wiki changes for foundry. With induction furnace, of course, you can melt all kinds of metal. But if you don't have that, then everyone has a stove, and you can use these simple alloys to do that. Like, for example, pennies after 1982 are made of nickel. Zinc. So you can make zinc alloys out of pennies. They just have, they're copper coated, but they're zinc inside. United States pennies. A way to make, easy access to molten metal. So let's see, zinc, let me see, stovetop metal casting is the page on the wiki. 900 Fahrenheit or about 500 Celsius. Not bad at all. 900 Fahrenheit is 480 C. Aluminum would otherwise melt at 660 C. So it's a little, again, to the top range of stovetop foundry. But that's an interesting point for easy access to metal at the strength of aluminum. Aluminum is about 40,000 psi. Steel is up to like 100,000 psi or more. But with 40,000 psi, that's close to mild steel, which is about 54,000 psi tensile strength. So, steel, that's hard stuff. This stovetop metal casting is 40,000, about 4/5. of steel in terms of tensile strength. Not bad. When you talk about plastics, they're typically in the range of 5 to 10,000 psi. Here we have access to 40,000 psi with stovetop. And then when we get to the heavy-duty induction furnace work with steel, that's kind of the whole new beast. But that's when you get super strong stuff. Now, I also was looking into this metal stuff because I am getting ready for this microfactory that can melt steel and produce tractors, full-size tractors, for $500, which means your labor plus the amount of energy it takes to melt steel in an induction furnace. But I was looking at aluminum/iron alloys, and it's like, why don't we ever hear them? Does aluminum alloy with steel, like with iron? Well, it turns out that yes, you can do that, but the stuff is very hard but brittle. Very hard but brittle, close to titanium strength, but very brittle. So people don't use aluminum steel alloys until a few years ago. In South Korea, Mr. Kim, somebody in Korea invented a process or innovated a process where steel aluminum alloys that are still soft, not brittle, but the strength of titanium. Crazy stuff. So I think I put that somewhere on the wiki as far as, let's see, aluminum steel alloy. But the point of that is, man, there is so much. So steel aluminum alloy page on the wiki, there's so much innovation everywhere that can happen. And that's why this open source stuff is important, because then we can unleash access to all this kind of innovation where a lot of people are innovating on this kind of material. But look at that, steel aluminum alloy. Yes, it's possible, high strength but brittle, until the Koreans recently figured it out how to make it not brittle. So you can take a look at that link. Just very interesting. Titanium strength from an alloy of aluminum and aluminum and steel. So they massaged it and rolled it in such a way that the structure became really ductile, light as titanium, strong as titanium, but simply aluminum and steel. Crazy. Okay. So that's a little update. I'm gonna feed in on the D3D version 19.02. So the CAD on that is absolutely finished. Not absolutely, but more or less. I had some troubles in FreeCAD on that. In FreeCAD 16, I couldn't get the second what do you call it, cable chain to work for me. But by and large, the design is finished, and I'm building that right now. I just want to show some of the features in a CAD file. So D3D V1902 on the wiki is a new little feature I put into the CAD part library. What I'm doing right now, so I seeded the whole library. All the parts are there, and there's some couple of small changes. But I also put this string of images up at the top, which was kind of like, in addition to the part library, the flow of which parts I made after another, so you can see somewhat of the evolution of the design as it went. And I just decided to leave that there, since all those images, like for example, if a part changes in the part library image, the icon will show the latest part. But if you click on it, like for example, this XY bracket with a hole in it, well, that's only got one. But let me see another one. What about this one? No, I'm looking for visual picture histories, because what's useful is, for example, if you look at the 1902 version final of D3D, click on that. Well, I don't know. There is no history, no visual history, like only the latest image shows up. But you do see some thumbnails also in the version history as well. But it kind of occurred to me that, okay, keep this clearly visible version, like visual history. That's a good thing. So I thought that was just interesting to put that in there. Okay, so let me talk about a couple of things on a 3D printer. This is it. It's kind of what it looks like. So this cable chain actually would join here, not at the other side of this. But okay, so this is a 12-inch frame, which means that it would ship inside a USPS flat rail rate box, but still achieves a full 8x8-inch print bed. How? By straddling the x-axis and elongating it on top. When I straddled it on top, I used this bracket here. Now you see this one bracket has a hole in it, and also this carriage here has a hole in it. Why? Because the cable chain wires, they're going to be neatly tucked in through that hole and through that hole, so they go into this final cable chain, which, as you see, didn't work out. This final cable chain, these pieces, they're pointed the wrong way. But achieving full 8x8, there's one little mechanism that I want to point out here. So right here, this is actually a secret to automatic alignment. Jen, you might remember we might have had some issues about alignment on y-axis, two parallel y-axes. Means that if the frame is off any at all, you will get binding on the y motion. So y are these axes, this axis here and this axis here. So looking at this machine, it's like x, y, z axis. Y is this way. X is this. That's the long with the extruder. The idea here is, even if the y-axes are not parallel, I put in this piece right here. This is a half carriage piece, meaning it has the bearings inside of it, just like the carriage, which slides on the axis. Right? What that means is that there's a firm constraint where the rods go into this half carriage piece, but if the y-axis, y1 and y2 are not parallel, this little the rods here can go in and out of the carriage piece. In other words, there's a degree of freedom afforded by this piece right here, which is a carriage piece with internal bearings. So the little bearings in there, there's bearings in there. So if the axes are not aligned perfectly, this end can slip in and out to allow that to happen. Now, you don't lose any precision or anything. There's still a very firm attachment on the other side. And on this side here, there is no motion in Z or Y, just a little bit of this X to adjust for the Y paralleling. So that's a good deal. That means the axes will roll smoother, even if you have poorly aligned y-axes. So the motion will be completely free. It will never bind up. Historically, we had to be careful about y-axis paralleling. This eliminates the need for y-axis paralleling. So this is one more step towards build simplicity. The other thing is, you see that once again, going back to these simple end stops, they're not showing the actual electrical piece, but that's actually very convenient because the ones we have, they stick out an inch from the original design of the 3D printer. They stick out an inch. These are a little tighter. They will take about half an inch of space. So it's more convenient to have a smaller end stop, which is also adjustable on an x-axis here. And same for y-axis, just going back to those end stops, simply because they're a little tighter, saving you about half an inch of motion space overall. So a little improvement on the cable routing, definite improvement on the y-axis parallel, definite improvement here. So here's the new extruder design, like you would see here. This is this part here. If you see this picture, this is how the new extruder looks. So you see the fan and the sensor in this nice tight arrangement. Removing the omnidirectional shroud. Omnidirectional shroud may or may not be better. The thing I don't like about the omnidirectional shroud is that it covers the print, so you can't really see what's printing when you start the print. So I like to keep it open. And now we're actually, thing I didn't mention here, this is now with a Titan Aero volcano nozzle. So you look at this here, that's the vertical nozzle. That's the tall one, the big volcano nozzle. I'm not showing all the other parts, so this file remains under one megabyte. but this is the bigger volcano heater block right there. This part right there. That means up to 1.2 millimeter printing. Theoretically, you can go up to 2 millimeter. I don't know how that works, but they do make 2 millimeter nozzles. I saw that. We'll see what the limits are. But the idea here is to max out the ability to print, so we have the full capacity to do rubber and metal. Metal comes from the metal processes. The rubber comes from 3D printing. So you talk about tractor, car, wheels, tires, tracks. If you look at, for example, a yard selling, where they sell agricultural implements, it's just a pile of rubber and steel. And here we address with an extruder like this, we can print the rubber. The goal, technically speaking, I was looking at some numbers. We want to get to about 20 pounds per day print rate of rubber. Right now, I think the best that's out there that I've seen is about 5 pounds per 24 hours of printing. I'm not sure that's in stiff filaments. That's not rubber. I'm not sure what rubber state of art is today, but I think it's more like probably like 2 pounds, 3 pounds. I don't know. But what we do want to do is, if you study what available extruders are for rubber, well, the Titan Aero is the best one, but it's still not optimized because it has this distance. Like the drive cog is like around like there. I'm not showing it here, but it's around there, which means that it has this distance here that I'm moving right now before it gets into the metal components, before it gets into the actual hot parts. So that distance there is where your rubber can kink up. Now, that's why they have a neck. The Titan Aero extruder has a neck there that constrains the rubber, but still, that's not optimal. You want to have the distance from where you're driving the filament to the hot part as minimal as possible. So that means bring this down or bring the hot elements up. We're going to have to redesign it because I don't think this Titan Aero is going to get us more than 5 pounds per day rubber print rate. So this looks like further OSE finagling or design work, where we're going to have to hack it and just go with some more design work on that. So that's about it. And idea there, I mentioned the zinc aluminum alloys and a little bit about the extruders, because it looks like we're going to have to gear up to make our own that's optimized for rubber and 3 millimeters. There's one that's optimized for rubber and 1.75 millimeter. That's called a flexion extruder. Eric Lotzi put that on a wiki. Flexion, you can look at that. But we want to go with 3 millimeters. We want to do bigger stuff, and we want to make our filaments. So that's why we want to do 3 millimeter. We want to do larger things. So it turns out, reviewing the D3D CNC circuit mill, that is capable of milling aluminum. That's pretty standard using the kind of 500 watt spindle like we have on our D3D CNC circuit mill. So we can mill parts such as the extruder aluminum pieces or the heater blocks. Because, man, the authentic E3D Volcano heater block costs you $20. So this little metal piece, it's about 25 cents of aluminum, costs you about 100 times as much. For the finished product, when you just add a little bit of information to that or machining to that. So there you go. That's the report on the update here. So the general 3D printer strategy, thinking about that, is, for us, it's scalability, modularity, and materials as some of the big values. So scalability, once again, going to the 1 cubic meter printer. Modularity means that we have the different tool heads, like the D3D CNC circuit mill, and we're moving on to the torch, and then other things like more milling and more laser, small laser. We never ended up building the small laser yet. We don't have that built. We know that we can just put this simpler head on and do that. That's been done pretty easily. So that's the modularity. And as far as materials, that's where the filament maker comes in, because then we can start composing filaments. And the latest thing on composing filaments, one thought to provide here is that there's a thing called metal injection molding. And that is where they use regular injection molding like plastic, but that plastic, the metal injection molding pellets, they start with pellets that are polypropylene plus the metal of interest. And what they do is they inject and mold it, and then they sinter it. They put it into an oven and burn out the plastic, and you're left with 100% metal part. So how about if we try to make 3D printing filament out of metal injection molding pellets, which already exist and are formulated just for that purpose? There's a company that does that. They go from pellets to a 3D printer. So their extruder is not a filament 3D printer. It runs from pellets, metal injection molding pellets, MIM pellets. So what if we try to do the filament? I think that's realistic. It turns out the carrier is polypropylene, and I mentioned about the high temperature enclosure last week, and polypropylene prints well in a heated enclosure. You can't print that well in air because it tends to warp up on you. You got to keep it warm. But if this polypropylene is the carrier, we can print this stuff well in a heated chamber, and then we can sinter it, meaning burn out the plastic, put it in an oven, burn out the plastic, sinter the metal. So that's at high temperature. Like if you're doing steel, that'll be close to like 1,000 Celsius. So that's an oven. But once again, going for routes for transitioning from plastic to metal, using the 3D printing capacity, which is down to sub-millimeter scale accuracy. That means hundreds of microns. Like 100 microns is 0.1 millimeter. That's the kind of accuracy you can get here with the 3D printing. The actual positioning accuracy of the system we have currently is 10 microns, as was shown in a paper on the D3D, the paper that Michigan Tech people wrote using our D3D CNC circuit mill, which has got the same drive system as the 3D printer. So that's a bit of product ecologies, and then moving on to materials. I still believe that we want to involve schools with this, so I'm getting pumped about taking this to schools, creating curriculum, stuff like that. I talked to Greg Gage from Backyard Brains. You can look at the YouTube channel. We talked about, he does really well on, he sells kits for neuroscience, and he does well on that. So you had a discussion, you can take a look at that, where he basically is able to get students to do meaningful R&D work in a model that's similar to OSE, which is that we want to involve the public in real R&D work, right? Which we haven't so far. I mean, not so much. I mean, a little bit we have. But I think we can involve schools in that. And then, so if you seed the schools with good content and real experiments, like for example, figuring out how to turn the MIM pellets into filament using the open source extruder. Yes, great research project. Tons of great research projects can emerge out of all this work here. So that's my report, and then I'll quit here and move on to others. Open source golf cart. Oh yes, so we will announce that. So 2 to 4, if you can make it, 2 to 4 p.m. this Friday, we will continue taking the CAD that we already have on the open source golf cart and assemble that into a working machine. So spend the time assembling that with the components that we have. I know we have the motors, we've got the frame mostly done. We need some more things. The power cube we can pretty much borrow and hack up for this, and then we can see how the thing looks with a solar panel on top, and examine the basic geometry. But that's a quick prototyping experiment. Okay, who else can pipe in?
So I was talking to a friend of mine who's in one of the co-ops in Eugene, one of the housing co-ops in Eugene. There's 3 associated housing co-ops.
Mm-hmm.
And we were talking about the house, and he's said he loves it, even though the 3rd floor bathroom leaks into the 1st floor something or other. And I said, well, if you had one of our 3D printers, if you built one of our 3D printers, blah, 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 not blah, blah. If you built one of our 3D printers, then you could use plastic water bottles and Hugh Lyman's filament maker, and you could print out the pipes you need. And, then like the other co-op could have, like a circuit mill, and then the other co-op could have this other thing. And he's actually really excited about it.
Yeah.
So I'm thinking that I don't think I'm going to be able to do the hackathon. I've got too much other stuff going on, and it'll mean I'll miss a day of work, and then I won't be able to afford to pay rent and all the big circle of nonsense. But I'm thinking that, and then, like I am still connected online with quite a few, like kind of extreme preppers and alternative history people, and they would be really super interested in a lot of the stuff that we've got going on. It's like I wasn't sure how fringe you wanted people in the project, but I think we're all fringe in a way.
We're all freaks. However, if you can do open source product development, all freaks that do product development for the open source are welcome.
Right. Well, yeah, I said fringe, not freaks, just to be clear. I wasn't calling anybody a freak. Speaking of on the edges of society. All right. Yeah, I think I'm gonna go forward and really focus on that. I haven't heard back from any of the homeschools lately. I'll give it probably another week before I'll really have time to sit down and go through a list again, and I'll do that. But then it occurred to me when you were mentioning your person who sells to homeschools, I know there's a few good science suppliers for homeschools, and maybe instead of trying to go directly to the homeschool programs, we could go to the science suppliers and find out from them what the need is, because they would already be hearing from people.
Yeah. Now, so for example, one thing that comes out, like if we go through a distributor, so I guess that's what a supplier would be, a distributor. So for Greg Gage's Backyard Brains work, the distributor charges 30%. You basically sell them the stuff with a 30% markdown. They take care of the rest. So that's a kind of cost we would have to take if we do that. So there's different ways to go about it. Like once you have enough production and you cannot push all your product out there, a distributor might be a good idea. Now, another model is, so what I'm thinking about is that there's a distributed effort of small producers. And I don't know if we go into the distributor route ever. Like theoretically, that would not be the ideal thing, because ideally the word of mouth would spread. Like if we're actually getting this stuff out there, getting into schools and serving real people, the word of mouth should spread. But yeah, it's debatable what will happen in reality. But at least initially, I'm thinking that each person produces. So the bottom line is 3-day kind of a production cycle. So here it is. So you make 12 kits in one day, and that's extreme production engineering, including quality control. So 12 kits in one day are built. If you're shipping them, it would take you another day to ship them. And if you ship them, you've got some customer service to do, so that's another day. So I'm counting 3 days to do 12 printers. Now, at the current rate of return, 12 printers is $3,600. So if that model works, and this has to be shaken down and proven as a replicable thing, then we're talking about making $3,600 in 3 days, so about $1,000 a day revenue, which would be amazing for funding the project. So imagine a number of people that can achieve that level of productivity and skill to be able to pull that off. It does require significant education to make that happen, but I think it's feasible, and that's the way I'm picturing it right now. Therefore, if you're working with OSE, you can be working like looking at realistic numbers. 9 days you're producing kits, so you do 3 of these production runs. Out of that comes revenue for getting paid to do this full time, and money for OSE to prototype more and grow the movement that way. So that's one way to go. If you include a 30% cut there on the distribution, that may or may not work. It depends on your sales volumes, but we'll see how it goes in real life. And of course, as time goes on, we make improvements. We make more of our parts, like the extruder, for example. If we were to build our own extruder, wow, that's $120 less on the cost of the printer. Now that would be a big feat, because that extruder has to be as good as the E3D and better. So yeah.
So I was thinking more just in terms of finding out what kinds of things they want that they're interested in, you know, getting free information from them. But then it just now occurred to me that if we were talking about before about having a paywall, if it might be worth the 30% to get the 3D printers out there. If like in the 3D printer kits, there's the option for like ongoing curricula with the paywall, and also like maybe a discount on the filament maker or the plastic water bottle shredder or something like that. So we could make a suite of products and then just kind of take advantage of that for just one thing. But that wasn't the direction I had been going at all. I was just thinking to get free information from them.
No, information. No, absolutely. The information would be good to find out the needs and get data on what's really needed. So absolutely, yeah. And then, so you mentioned about, you know, maybe curriculum is behind a paywall, or maybe the other way around, where the hardware is behind a paywall, obviously, but the curriculum could even be free. So imagine we're getting quite popular because we produce decent curriculum, and then if you want to do experiments, there's hardware involved. So that's where the hardware could come in. And that's how Greg Gage from Backyard Brains says it works. It's that he provides research and development. People want curriculum, they buy his kits. So there's different ways to go about it. But it seems that, like, what do teachers need? Like a lot of people are saying, a lot of teachers are pretty busy and maybe not jumping out of the box. They want ready packaged product. Yes, a distributor would help there, because I heard from Greg that, yeah, the distributor makes it easy, you know, so things like that. It makes me think that business development, like, we should be talking a lot more about, at this phase, about business development of all the stuff that we could be putting out there as products and kits. So that's a worthwhile discussion to have.
So
yeah, my brain just fired off.
I saw what was that, Jen?
Greg Gage?
I saw the thing with Greg Gage.
Yeah.
It seems like the neural sort of kit stuff, which they do have nice markups on those, that's for sure. But I see that he said
nice
that there's
markups. Wait, hold on, man.
Understand that they have you know, there's not a lot of, I guess, the science kit industry is obviously not very competitive, I guess is one way to put it. But
no,
because it sounded like the competitors have really even higher markups, is what he said. But it's
he said 10%, like his cost is 10% of the competition, which was like, holy cow. All right.
And then there's markups by the distributors and all that, so they're all getting quite a bit on the whole kit system, which I can see. Plus the price, it didn't look that bad. I looked at a lot of some of their more complex kits, was like an Arduino, a board, a shield or something. And I can see how that's a niche where you can do real science that you can, you know, write a paper on or whatever, like he said, where it's kind of hard. I mean, the OSE thing is more like trying to get people to sort of join the construction of things in a collaborative manner. And I don't want to say education is just kind of, it's a little, well, it's not that it's just dumbed down to the point that it's hard to do that. I mean, there's lots of, you know, there's always been shop classes and you know, students do, you know, older students do welding in high school and all kinds of things. But it's, well, some of it is the convenience factor. I think it always a lot comes back to the convenience factor. People would rather, and institutions included, that they want to buy a package and then there's just a 3D printer to have for students to use or something. They want, you know, quick turnkey solutions with all the nice software and these sorts of things. That stuff sells well with businesses and probably education institutions too. That's probably, often the convenience issue, I guess, is a thing that OSE is kind of up against more, maybe.
Nepotism. These people are selling to each other. There's district-wide contracts, and the science stuff that's getting purchased is getting purchased from somebody's friend. I do catering. Some of the events that we cater are actually school districts meeting with vendors. Basically, it's just they get together and they drink and they talk and they just hang out and be friends with each other. So the next time somebody needs some duct work done or needs to order some, I don't know, test tubes or whatever, they're thinking of them first. It is not based on cost effectiveness. It is not based on quality of product, and it's not based on usefulness. What school districts buy is based on who knows who's got friends, and who gets their foot in the door and buys the guy a drink. And I'm really sorry it's that way, but that's the way it is.
Yeah, that's what it looks like. It's a networking thing, and there's probably very few things available to some degree in that space too. So when somebody knows somebody, it's a niche and something that fits the potential for some educational tools, then that's what they buy. So I don't know what I mean, we can make all kinds of kits and plastic models and maybe some functional stuff, but I would think maybe I guess you were saying more like the service or the curriculum, and that could be interesting. But I think an issue there is if it was like a really nice, easy to use website or something, or some software behind the scenes that created a sort of a curriculum interface where you could get students to do like projects where everything is broken down and it's easy, and then it could be the little pieces. They could pick a little piece or something to do. If there was a good software interface that managed all that and made it easy for any student, then that would be workable. But that's a big problem to solve in its own. So
well, I mean, the opportunity is, as I was talking about, the idea that a lot of this can be turned, like, take any piece of innovation like on the printer right now. Think about a printer kit or some education around building a 3D printer. So say the OSE Club's idea where we teach teachers how to build and use the 3D printer for the classroom. So what kind of curriculum can you generate around it? Well, anything that's got to do with, so there's mechatronics, electronics, programming, building things, STEM, all of that. So take a look at an example of what's the next step on the extruder. Well, getting informed about how an extruder works, like William, take William, he's open sourcing the extruder in Canada. There's a simple version, and maybe that we could do a project where you actually design a different version of extruder as an initial example. Then you can take the same machine with the CNC circuit mill and actually mill the pieces and all that. So there's a whole ecology of curriculum that can be created around it, and then some. Because a lot of the stuff, so take, for example, the MIG casting, right? I haven't done it here. Well, it's a thing that as soon as we have the idea, and there's 100 ideas like that, right? Like, think about all the stuff we talk about here. There's 100 of things we can be doing, and that's why I think the armies of students who are doing this as kind of like data taking projects, and then imagine integrating that with publishing papers. Like, you're actually doing an honest assessment of metal injection molding, 3D printing filament. I mean,
you can't get that into the schools in this country. Teachers don't choose the curricula, and and they don't, and curricula isn't based on what people are learning. It's based on competencies that can be checked. I mean, that's why I homeschooled. My kids did a little bit of public school here and there, but the teachers don't have any flexibility with the curriculum. It's not just like getting the money to get the 3D printer in. You might be able to get, I would love to see it, but you're beating your head against a really big dead cement horse.
Yeah. It could be, but that's where the answer could be, okay, well, that's the schools are not necessarily the market. It could be that the homeschools are the market, or any other, or alternative schools, or whoever else. So
Yeah.
there's has to be that kind of penetration of the market to just find out our sweet spot, where we can exist and how we can exist. But like, take William, and he's at a high school that's largely based on international students, but he's very successful in his STEM program. I mean, that's in fact why they're keeping him around. He said because he started the STEM program with a 3D printer years ago. It wasn't our 3D printer; it's actually one of those that you see in a picture. His school got really interested in that. So there's outliers, people like William, who do have a different agenda and who actually go the extra mile to do things differently. And then again, there's a lot of, think about the first robotics, right? Everyone does first robotics, and starting an effort similar to that through a movement like OSE clubs. So I mean, there's tons of possibilities. The question is, where do we start getting some traction?
I keep forgetting. I think like Future Farmers of America and 4-H would be good places to really push.
It does seem like the younger students in primary schools are probably a little harder to get inroads in that. And it sounded like Greg Gage was suggesting that was mostly for undergrad students with the neural link as well, which sounds, it seems like this was fairly simple equipment, but I could see meaningful stuff coming from that. So yeah. It's kind of how do you make kits that are, or I mean, in this case, it is kind of more the 3D printers and things like that, or a lot of it is also the whole ecosystem, so it is more of like a classroom or a lab type setup, because you want larger machines or the full ecosystem of machines. Because a lot of it is getting the design.
But I mean, see, Abe, I think the enabling part is the modularity, right? Because you can take any project and break it down into a very small part. So, for example, say you got the 200 kilowatt induction furnace for the village, right? That might be a little too big for an elementary classroom, but what isn't? What about an Arduino with a few MOSFETs that make a small scale inductor that you study? You actually build that as an experiment, and then you can talk about, okay, how do you scale that up, and studying the scalability of that. You can break things down into very small chunks based on modularity of understanding the technology to just break it down into very simple parts. So there's different ways, and I do see just huge, like, I didn't see this before, but now I definitely do, where there's just take every micro component of the stuff we do, and that becomes a potential project that could be that, okay, pending, okay, we'd have to get this into the school somehow or make it actually work and make people interested in. But if we can succeed at that, there's a lot of stuff that can be done that's actually meaningful feedback and data on all the work that we do, simply by the fact that, as I was mentioning today, that there's so many different points of innovation to make. Just tweak this little thing or this other thing, and you have things that can be the same yet very different. There's a lot of tweaking that can be done. So
anyway. Oh, go ahead. I'm sorry.
I was just going to say the mass micro collaboration, sort of distributed collaboration. Always the thing with that is kind of, it's getting all the pieces that kind of go with that, getting software and stuff, and making it easier for documentation and the important side stuff that it's probably often you can get students or anybody to do any of that stuff, but it probably needs an interface and setup that's fairly clear for students. And I guess maybe the teachers, and of course people, if you're trying to do that in an educational system, they can kind of help set up some of this stuff and define some of the parameters and break things down, and that's a good way to look at that. But I imagine for teachers and so on, it's a matter of time. So they like predefined curricula and things that are readily available.
Well, what does that mean for us? That means we got to do some packaging, right? That's called business development.
But part of business development is knowing where your inroads are.
Yeah.
So, and I just really don't think I think it's going to be a whole lot of effort for the return on that one. I have a question about, okay, so like if I had like a scaled up 3D printer, can you actually take off the part that does the printing and put on something that does the milling on that? Are they similar enough that you can, like, if you have the framework and the axis, that you can change between the like the printer head and the mill and the laser? Can we do that?
Well, for the tiny mill, yes, because we've already done that using essentially the same kind of axis system, and the laser, yes. If you talk about heavy duty machining, then you would need the fatter universal axis, right?
Right.
So, but you can design any kind of a crazy Frankenstein out of this, because it's all a construction set. So you can have if you look at the universal axis page, for example, you see the 1-inch axis with the small 3D printer axis on it. So you can mix and match them too for different purposes. It's infinitely playable and stackable and so forth. So that's the beauty, that it's may not be super obvious to a beginner, but that's where you have to package it and say, okay, this is a construction set like Lego, because that's what it is, and it's hardly visible. You can't see it unless you really study what this thing is like.
I think that we can. I think that if we can get this into like one group of co-ops, that it'll spread across the country and around the world, and it'll be a natural growth. It was just a matter of like reconnecting with the people in this one group, and then it's a national organization with international legs, and it's already a group of people that are trying to do things themselves and trying to cut costs and trying to save the environment. You already have the ideal built in there. The risk that we run is that somebody's going to like free CAD plans for guillotines and 3D print that stuff and, go out the rich. But I mean, that's not us.
Yeah, well, the challenge is, and I can tell you this, I have a lot of discussions on this topic, and the first thing you ask, what is your license? And the license clarity, like, okay, take a co-op, because, for example, we cannot work with L'Atelier Paysans, those people who make so-called open source farming implements in France.
Yeah.
Well, they're not open source, they're non-commercial, so we can't use that. So a lot of times you have to ask. Let me just throw you this link so you can appreciate the story here. So it's under the NC page. Everyone's this is required reading, the non-commercial page on the wiki. There's an example, there's a comment on, so if you look at my screen, this was on Facebook. It's a discussion that comes up all the time, but you need to understand this before you go, Jen, before you go contacting the co-ops. So make sure you're very clear because a lot of people will say, yeah, we're open source, but it turns out they're not. So you have to ask them very explicitly, what is your license? Because if it's a
I'm talking about the student housing co-ops, and it's just they're not even it's just groups of people that are. I mean, It would just be students. It's it's not.
Okay. So that's definitely so that this heavy argument applies somewhat, but if we're talking about, because what I was thinking is, go out to other groups that do this explicitly, like they're open source product development groups. The only one that I actually know of right now is Public Lab. They have kits and they're fully open source, OSHWA compliant. But what I was saying is that you're going to be hard pressed to find entities that are actually open source. A lot of it will be like non-commercial or peer production license, which is also not open source. So a lot of the peer economy guys tend to not be open source as well, unfortunately. But yeah, if we've got a co-op of individuals who are into this, yes, absolutely. But then again, if we talk about these people getting involved and sticking around to do further development, well, it's going to mean that we're actually developing further products, and that's where you also have to be very clear about the license too, because you'll see that a lot of times people will go along and then they'll make their own product, and you'll never hear from them again. So that's a thing you have to.
I think this would be people doing it for like personal use within the co-op, and then telling other people what a great idea it was and how much it helped. I'm looking at getting the micro factories into communities. I think we're ready to start that.
Yeah, we're almost there. So yeah, I mean, we can, as far as development, yes, I mean, get everybody on board to develop stuff. Help us develop more stuff. So the discussions are definitely worthwhile. Early adopters and all of that. Okay, Abe, I think you've got. Let's switch topics and go to Abe as far as.
Yeah. So back to the printer. I guess I've downloaded your file too to look at that. So that's I guess questions there. I started doing. The only thing I really got done recently was a little bit more added parts to the full assembly to check some distances and things there. And I just grabbed some parts files that I had. So they might be a little dated. The file got a little larger because of the extruder I added there. That was a few megabytes. For some reason, it's complicated. But I added kind of like those basic motor, the simplified versions of those motor parts in there, just like you have in your assembly. And I see you've modified a number of things, I guess, on the new one, which is interesting. And it looks like, actually, if I've seen what you did there, you actually modified one of the universal access parts for a through hole. That's, I guess, one of the last things.
Yeah, that's just because it's really convenient to get the wires through there. Otherwise, it would look kind of messy. So I'm actually looking at the final wire routing. Mm-hmm. But it's the identical piece, just rip a hole through it. And that's just that.
It could be a unique part then. So that's just for that spot.
I actually put it in a part library. I put it under the carriage. So this is under D3DV 1902. Go to the part library there. It's there. It's under the universal access carriage, and it's the modified version, which just has the hole in it. So,
so I guess my point is it's a unique part specific to that version and to that axis there.
Yeah,
it's the only part. So you end up printing a different part just for that, right? It's not it's a different part for included into the universal access. So I've been wondering some of the different versions how. I think John was pointing earlier, I didn't get any magnet spots on that clamp, and he left a note there for me about that. And I had forgotten about that to some degree, but the shape of it is so odd that it doesn't do that. And I know you've been talking a lot about people didn't like the magnets as much, and it looks like, with this design and the assembly here you don't need, and I guess you still have a metal frame and you can attach with magnets, but there's probably ways you could work around that. Are you thinking of moving away from the magnets for a lot of the things more?
Well, yeah, I mean, the holes in there and the pieces are there. De facto, they're still there, and sometimes they're used, but they can be used. But no, if you want something that's got contact machining, no. For a printer that's experimental and reconfigurable, yes. So that would be one of the many variations, but the official version, I wouldn't put it on a main trunk release, like say the kit that we do right now. No magnets, just very simple, because the frames are already CNC cut to accommodate the holes for the through bolts.
Yeah. Okay. So bolting stuff and less magnets. That's kind of what I'm wondering if on the universal access, obviously, at some point, if
look at that,
changing away from the magnets enough, I mean, again, we wanted to keep the universal access design a little more static, but it could be interesting to do. Maybe it's time to think about different designs on those options, especially looking at this PVC. Like you made a new versions of the shorter end stops. You were saying there. I see they're a little bit simpler. On the PVC, smaller. I'm looking at it there with that one magnet mount point, and from the beginning I was measuring, and it looks like those work better there, probably because they're longer, and because of the thickness of the frame itself and the position of things, it's like you probably need the longer end stop. So things vary depending on how, you know,
yeah. That's exactly.
So,
But the current end stop is completely adjustable, so it can be short, it can be long. You can put it wherever. So that's the cool part about it, is it's adjustable.
Yeah, I assume the switch itself, it has metal stuff, that there's some room to work with that. Because I know I measured what it looked like in the CAD, but the CAD, of course, will never be exactly as the same as the switch in real life. So what I measured on those switches with the metal
well,
lever looks.
Yeah, I mean, this is really cool. I like it, but go update to the new extruder. Well,
okay.
I would say actually take William Neal extruder, because that's the one that we can make pretty much ourselves. This one, the problem is in the way it's mounted. You see how it's seating on the clamp, on a seat there. The bolts are not good enough. Like what we ended up, that will end up coming off. Like if you're going really fast, they'll just shake out of there after some time. So in the version just before this one, I just put some epoxy there, like on the lip there, because you can't keep that motor in. It's got a lot of inertia. So
yeah, I think I pulled that out of a file that was a year or so or two old, so that's outdated. But yeah.
But this is, this is cool. Like for a low-cost version, the Titan Aero, which is $120, is probably not the right thing to do for a PVC low-cost version. So, but yeah, that's pretty cool. I'd say, this would be ready to become like kittable or, like marketable or something, like with the new Williams extruder, the fully open source one that we print ourselves and make ourselves out of simple parts. Because the thing about these two, like, as you look at this one, they can, like, when you this online, in this thing, and it can look different in the different versions that you buy. Like, for example, the neck is shorter or longer. It's your typical Chinese sourcing stuff. So if we have full control over the dimensions and regular step, making an extruder like this quite feasible. Part of the reason why we went away from this was that we couldn't get the same one, and then we also had to, like, the way we had the sensor probe mounted, we had to modify so we can mount it on fan. So we had to actually cut off some of the aluminum. So there's a few refinements like that make this kind of a pain in the behind to work with. But once we address those, that's why I'm suggesting Williams as a good, I think probably next. If you spend any time, just start putting together those pieces from William.
Okay.
It'll be a good collaboration.
Yeah, I'll do the extruder assembly, and I still got the bed and so on to get in there. And I wasn't too sure.
Yeah.
I was kind of going based on some of the old CAD, which way things should face. And I know most of the time the motors were on one side. In this case, the issue right now is it makes it heavy on one side, and I'm worried if it's possible, it probably wouldn't tip over or anything like that. But because it actually ends up resting on the bottom of that clamp at one point down there, it might tend to rock around or something. And if it was moving in operation that way, but I think we talked about that before. Maybe some feet on it or something. But also that to maximize the print area, I wasn't sure if there's obviously different ways you could attach or face the extruder. And then the motors, I was trying to see whether they clear certain points where they might hit the frame or the clamp, it looks like. Things like that, because they could be configured or attached.
Yeah. And that's exactly why I do all that in CAD pretty accurately, because, for example, the machine I did in CAD, I took dimensions off of that to build. I'm building it right now. And it's accurate that it's a working real CAD, not just BS CAD where it's just a concept. It's actual, shows that I actually was very specific to get the exact 8 by 8 inch bed area by designing that in CAD and making it exactly right in CAD. So that's where you can do that. You can figure out for this, I think we could be happy with like a 6x6 platform where you just make a nichrome heater, just wrap some nichrome wire and stuff. So that would be an easy way to do that. In fact, if you get insulated nichrome, you can use like a 6x6 inch steel plate, small plate. Actually, we have cutouts of that from the frames. And then you can just wrap the nichrome. If you use insulated nichrome wire, they have that. So you can literally wrap the wire around that and put the, if we use PEI on top of that, but PEI is an advanced option. If we do a heated bed, or of course you can do it without a heated bed, meaning just plain plate. So for the low-cost version, simple painter's tape works well for ABS and PLA. So that would keep the cost down on that for a very low-cost kit.
And I think I saw for the bed, it looked like in the new versions, the easier way to do that is to literally just clamp it between some axis parts, right? There's just rods that go through the z-axis and then just clamp it between axis parts, right? So I guess
you just put the rods into the holes, like that's your idler piece. Put the 2 rods in there and put the plate right on top of that. If it's 6 inches, it won't sag on you. Yeah,
and then I guess let's see. The general question, of course, is where is the 6-inch bed area? Because I guess that got to figure out a clear space for that where everything prints and can move. And then generally that has to be determined, because I assume some of that has to be configured in software. I mean, there's a certain amount of automatic stuff, but I assume there's some software configuration to do.
Yeah.
So you have to figure out where the print area actually is to define that better.
Well, it's easier. The soft part is easier. The hard part is getting it to actually move and not hit anything. If you want to study the range of motion analysis, look at my file, and as is, it's designed in the correct place, and you can trace how, okay, if you move the axis all the way one way, it hits the bed, and it's all arranged so it's geometrically correct for hitting the bed at the right place. But here, that's all that work you have to do here.
Yeah, I see.
And basically, you can do that as simple as, okay, so now I see here, for example, the axis is one. If you keep this carriage piece movable, then you can actually slide it left and right, and you can see where things hit. So you can actually move the whole thing, and using draft.
Trying to design my part assembly so that I could easily modify that kind of stuff and it would update. And I haven't really tested that too much yet to see how much they move around, but you can just do measurements and look at stuff. There should be a certain amount of, to do more animation and things like that. It's like you need to have more individual parts and less simplified assemblies, of course, is the issue, but that's not necessarily that hard to do either. So
if you want to see a way to do that, my whole file is under a meg. It's like 700 or so, and I've got these pieces as individual, so you can take a look at that for how I did that.
Oh, yeah, I see that in your file there. Yeah, I'm seeing different things in that file there. Actually, now I'm trying to figure out what you have going on underneath the bed in your file there.
Yeah.
You've just got some parts stacked.
Well,
I guess they're not.
The bed wouldn't reach the nozzle.
What's that?
Yes, the bed is raised because otherwise it would not reach the nozzle the way the geometry works out. So it had to be elevated a little bit. And still the same, it's a stack of idler pieces.
Yeah, okay, they're overlapped, it looks like currently, but that's,
Yeah, because I was using a whole piece and I needed a half. So I'm using 3 pieces, which is 1.5.
You might have to, so in other words, you probably have to print a part for that purpose, I guess.
Yes.
And so generally, well, if the bed is a certain size, I don't know how you'd make a parts to clamp that differently because it's
Well,
taller.
all we're doing right now,
so you'd have to make some custom stuff.
yeah, we're not clamping. We're using right now the method for doing that is we put spacer nuts. So we put 3/8 inch nuts
Oh.
over the rods and just
Right.
JB weld them to the aluminum
Epoxy.
plate.
Yeah.
Yeah.
Okay, I saw that method too. Yeah. Okay.
Yeah.
Yeah, I guess some of the stuff in your CAD file there is just to get it, to where it's spaced out right and so on. So
Yep.
yeah,
All the
it's not-
spacing there is correct, including
not-
that.
not the
as you see
final parts, but it's kind of laid out correctly. Yeah.
Right. I'm using simplified parts with accurate geometry.
Okay.
So they are in the right position. Like, for example, the X-axis mount to the Y has got that angle bracket, and that bracket is actually the same as the Y-axis to the frame connector, if you look at that.
Okay.
But yeah.
So you said this is a 12-inch version as well with a 6-inch bed, so that's
No, it's an 8-inch
similar.
bed.
Okay, an 8-inch bed.
So this is optimized for like the smallest frame that still has a huge, not huge, but 8-inch bed. So that's pretty if your outer frame is way bigger than the bed. This is like just 4 inches bigger than the bed.
Yeah, okay. See, the outer frame is 12. Yeah.
Yep.
Okay. Yeah, that's somewhat similar to the PVC. It's just, the frame
Yep,
is
similar. Except you're going to get, I'm estimating the way you are right now, you're going to get probably like 5x6 maximum movable distance.
the print area, or
Because I did the trick where I straddled the X over the top to get a much longer motion on the X. So that's, you're doing that between the axes, which reduces a lot of that space.
Mm-hmm.
So you can use this trick or keep yours. Now, the nice thing about yours is this is like even more top heavy, right? It's better when it's nice and compact between the carriages. So this is not as elegant because it's like all the components are outside the frame, but that's the way you get a bigger bed out of a small frame.
Yeah, and I guess the X-axis rods are a lot longer that way too.
They are.
So
yeah,
let's see,
they turn out to be 17 inches while the frame itself is 12 inches.
Oh, and you have two. Oh, I just realized you have two Z-axes. Okay.
Yeah. I do. This is a professional grade printer. This is a pretty high performance printer.
Yeah, more precision. Okay.
With a Titan and with the Volcano nozzle. Titan
and
Aero.
the motors. Huh. Okay. So, and you still got plenty of motor connections, or they're just hooked in parallel. Huh. Or yeah. The extra motors. Yeah. Okay. So, yeah, they don't add a lot of power, I guess, because they're not really doing much. Z-axis motor, right?
When you're going fast, like standard speed is 50 millimeters per second, this thing, I'm aiming to show printing at 300 millimeters per second. That is blazing fast, and you see this thing will probably fall over. That's really fast. You need those motors like that. Yeah. The inertia is huge. So that's where you have to reduce your acceleration if you want that to work. Like there's acceleration setting in Marlin. But yeah, that thing is going to be fast.
Yeah.
So
I guess normally there aren't a lot of quick, long motions, but I guess there could be. I'm short, tiny micro steps, right? So you're saying it would rock around.
You could go
because of.
Well, it depends how big a thing you're printing. Like if you're printing an 8x8 square, it's going to do, for example, the infill inside is going to be 11 inches of travel.
Yeah, I guess that happens pretty fast then on the infill. Yeah. But I guess it's the Z-axis that doesn't do as much motion. That's
that's super slow.
Yeah, actually, One thing I was wondering about on the precision on the printers, we keep talking about that. I've seen people printing, I guess there's different benches and so on, but for the accuracy, have you tried things like the hinges, not necessarily living hinges, although I guess those are a precision thing too, and sometimes they're justifiable if you're doing something that it's not going to last long for prototypes or something that you recycle right away. But I've seen them printing like functional pin hinges, and I get that requires quite a bit of accuracy. Is that something that you've tested on a bunch of printers yet, or?
No, I haven't done hinges. Where do you want a hinge here?
Well, I don't want a hinge, but I was curious what the you said this one is probably more accurate and faster.
Yeah.
The pin hinges, I don't know how much extra they require even compared to living hinges. Living hinges might actually be harder, but the pin hinge functionality is probably sounds like something that a lot of people would want to be able to print. Because if you can print, simple containers and things that have
that's no problem. Right. Yeah, that's easy to do.
Yeah, it looked like I was kind of surprised with that. You can just print them out as a single part and they just function.
Yeah.
Which
that is
was surprised.
The cool thing. Like
that works.
Yeah. Some of these things, like things that have internal joints, including planetary gears printed in one piece. Yes. It's pretty amazing.
I've seen gearboxes and they use PVA usually for that kind of stuff. And then you use water to melt that out. But I was kind of surprised they just printed and they were pretty usually freely moving right away that way.
Yeah, no, that is pretty amazing. So
I want boxes and things like that, enclosures and so on.
I'll show some of that with this printer. So
how did
I want to get good documentation.
How much clamping force did we have on that? I see the photo there. The clamp.
I didn't have any clamping force.
Not much.
It wouldn't stick. It would be loose. I mean, you can kind of see it there. See that little gap there?
Yeah. Is that the 2 millimeter version?
I didn't try that yet, so I might have to try that.
Oh. Is that so? That's the 1 millimeter gap.
Yeah.
Okay. Yeah. As I said in the email, my only concern was the strength of the bolting face. I think on the 2 millimeter, because there was a really thin area there where the bolt head would sit against it. If somebody torqued it down, I wasn't sure how well that might.
I gotta do the other one. But what I'm seeing is the PVC 3D printer king. You should go forward with it and get the $100 and build it. I think you can get one of these things down to, I think, $160.
So the frame and parts, what that, you think that includes?
Yeah, if you have access to 3D printing, so you're printing your own parts. Yeah, look at the D3D Simple BOM.
Okay.
Simple. Simple 3D printer BOM on the wiki. I added another one. So current one says 186 plus extruder. The recursion version, which means that we're starting to make the aluminum we're milling ourselves, $101. Making our own extruder. Go through that. Let's see. Most expensive part is four motors at $8 each. Controller is still $20, but everything else is printed, like belts. Do we have printed belts? Yeah, the belts are not even there because we print the belts and sprockets.
Well, so you need to get rubber printing.
Rubber printing.
You need a runner, and then you're saying on I guess on the making your own extruder, the parts they would make would be actually milling some aluminum blocks for the extruder itself, right?
Yeah, milling. That may be an overstatement because you can do the simple one like William is doing. It's just a block, and you need to do holes and tap them.
Mm-hmm.
So that's less complicated. If you do one that's really advanced, like the Titan Arrow, yeah, you do some milling there for the fins and stuff.
Yeah, I understood they were trying to shorten and simplify the extruders a lot, the pathways and so on.
Who was that?
I'm not up on the extruders. I think I heard about specifically the Titan Arrow. I probably watched some videos or something about that.
Yeah,
the newer versions.
And yeah. I mean, their current version is so-called optimized, but it's not fully optimized.
Yeah,
like after looking at
there's a lot of ways I guess you can make you've got to mill it more if you want changeable nozzles and all that kind of stuff. That requires some tapping or some manual boring and tapping that way, I guess. It's changeable nozzles, or I don't know if there's anything that has quick change nozzles or anything like that. That's probably not very feasible.
No, I'm not
being
sure how you
able to
do
change
that.
nozzles, I don't know how you would make it work.
But probably that could be a perfect invention for the homeschooler from Alaska.
Figure out that,
Mm-hmm. I mean, they have quick exchange high pressure couplers for hydraulics that are at 5,000 psi. I'm sure somebody could figure out a system for this.
It's probably just
never even thought about that one yet.
Of precision machining that's required to make a type of screw
it would be.
fitting.
I'd say it could get away with as good as for hydraulic quick couplers, because say you do that sealing part in a cold part, like make it reach all the way to the cold part, so you're not exposing that to heat, and it still kind of like snaps in kind of hard, and it's got the sufficient contact. That would be an interesting thing. But those parts are so small that it's hard to do that, so you have to expand their size probably.
Yeah.
But I mean, definitely hackable and doable. Like I was thinking about, let's make those necks and parts bigger, so we make them like, I was thinking we can eliminate the neck, meaning eliminate the part that leads from the filament where the filament is driven to the metal parts. Eliminate that by putting the drive cogs so close to it, right? What if you eliminated the heat brake altogether? A heat brakeless design. That's a crazy concept, but nobody's done that. But you still need the thin section. But I was thinking, okay, well, why don't we just make that thin section part of the nozzle? It's a long tube that just screws in all the way to where the feed is, right on top of the metal. That's a crazy thing. It would require a thicker nozzle. And it would have to be probably steel. So that's hard to machine. But
it's been a little bit since I've seen much videos about the extruders, and I don't have experience with it. So the thermals have to be complicated almost. If anytime you change anything, I can imagine the prototyping is hard to requires a lot of time testing, because the thermal variation on stuff has got to be complicated for different types of materials.
That's getting a little ahead of ourselves. We'll get into that, because I do believe that the extruder construction set, well, first of all, the extruder, bioplastic extruder, is part of the Global Village construction set. And that kind of, if you take the whole product ecology around that, that means extruders of all sorts, including the extruders that are used to make filament itself. So we'll get much more into that in the future. We're not really there so much yet right now. Okay, well, let's keep rolling on here.
All right.
I want to see. So thank you. Keep going. I would say, Abe, the biggest suggestion there is just take the parts from William and start composing that into a working extruder. But that also means we're going to have to remount the probe. So we got to remount the probe and a cooling fan. Print cooling fan, yes. You'd like a print cooling fan. You don't need it, but it's way better with it.
Okay.
So an assembly probably similar to mine. You can look at what I did on a probe mount / print cooling fan mount. because that system, an old system, still does not have a cooling fan, which is not right. So you're going to need to accommodate both the cooling fan and the probe in the design that William is open sourcing. So the work from William is not done yet. It'll be a perfect exercise for ample spare time and free CAD.
Yeah.
Thank you. Eric, do you have anything to feedback on? Eric, anything from Eric? If not, we can continue. Okay, so let's wrap up here then. Good meeting. We're moving forward on all kinds of things. So Friday, it will be our next session, 2 to 4. Let's call it 2 to 4. I'll get that note out. 2 to 4 on the open source golf cart. We'll finish up seeing how much of the CAD we can compose together. And otherwise, next meeting on next Tuesday, 2 p.m. Central, same time and place on Jitsi. So thanks, everybody, and we'll meet on Friday again. Take care. So yes, please upload this, save this and upload this to YouTube. Thanks, everybody.
Okay, good meeting. Later.
Thank you.